let's get started. All right, so PS5 is out. Due Thursday or Friday. Whereupon PS6 will come out. Be due the following week, and then PS7 will come out. But it'll be due 2 weeks from when it comes out, because there's a midterm on March 1st. So it's sort of a 2-week assignment, but you've got to study for the midterm in there too. And remember, PS7 will be a pair assignment, so we're working on that, finding a partner. It's not optional. Are there any questions or problems before we start? Okay, so what you're supposed to be doing on PS5, crystal clear? Anything you're hoping someone else will ask? Okay. Last time we were talking about multi-threading, multitasking, and I want to continue to show you some more examples today. This up here is where we left off. So this was an example, if you remember, of a method that, this method, you call it with a parameter n, and it decrements the property total n times. And this one here, increment, works similarly, but it increments total n times. Up here in this compute method, we start one task by calling increment. So we got one task that's busy incrementing, another task that's busy decrementing. We start both the tasks, and what happens here? Yeah?
What does it mean to lock the item by putting a curly brace over it?
It means well, it's commented out right now, so I'll address that when I uncomment it, but I'll definitely get to that. Okay, so what's going to happen with this highlighted compute method? We start one task, highlighted area. Okay?
Keep checking and waiting for either one of those to be completed.
Right, so, well, I'm waiting for both to complete. So that's sort of, all that loop is doing is it checks if either T1 is not finished or T2 is not finished, the loop continues. And what it does is it writes out the current value of that total instance variable, and then it sleeps for 500 milliseconds, half a second. Why did I have it sleep? Why don't I just comment out the thread.sleep? Yeah?
Otherwise you get a ton of print lines constantly going on.
Certainly I get a ton of print lines, and I'd be wasting a core to do it with. I don't really need to be checking them frequently. Half a second is good enough. So every half second I wake up and sleep. So this, how many tasks does this program have? Yeah, I got a 2, I got a 3. The 3s have the majority. So yeah, it's 3 tasks. There's the main task, the main thread. You call main, that starts a task. So it's doing its thing. And it spawns 2 other tasks. So while those tasks are out spinning, doing their thing, this one is doing its thing, which is to wait for half a second and see if the other 2 are done yet. Yeah?
What's the difference between thread and task?
Task is an abstraction that C# builds on top of threads. So just tasks are a more convenient way to deal with threads in C#. For our purposes, they're basically the same. Finally, when both the other tasks are finished, the main task prints out what the total is about. And what did we find happens when we ran this program? Yeah?
Some of the increments and decrements would conflict with each other, and so total is nowhere near the 0 we thought it was going to be.
Right. You would think that if we add 10 million, if we increment 10 million times and decrement 10 million times, that we'd end up with 0. But in fact, we saw that we didn't. So just to remind you, I'll run the thing. And you can see right now it's more positive than negative, and they both finish, and it ended up like 4 plus million. And if you run it again, finishes, it's 7.5 million in
What
arrears.
does sleep do?
Sleep just suspends the task for 500 milliseconds. So the parameter tells it how long to take. Sleep pauses for a certain amount of time.
Okay.
Okay? And what we saw last time, the fundamental problem is that that plus plus operator, one place we're doing total plus plus, the other total minus minus, the technical term for it is not thread safe. And we'll talk about what thread safety means with a few more examples. But the bottom line is, it's not a single operation. It's not an atomic operation, indivisible operation, because plus plus involves reading the value of total, adding 1 or subtracting 1 from total, from that value you just read, and then writing it back. And so when we've got these two tasks running in parallel, reading, operating on the result it read, and then writing the result back, those can interleave in any way. It may be that, what you're thinking when you see the code is that, okay, one reads, adds, writes, the other one reads, adds, and writes, and they take turns doing that. But they don't. One may read, then the other may read. Then one increments, one decrements, and then one writes, the other writes. So only one of the results will be reflected. The result gets overwritten. That's the fundamental problem. Now, what way did we have to fix this problem? In other words, to make that plus plus operation atomic, indivisible. Yeah.
You have to lock the thread.
Okay. So one way we did it was with a lock, which is what the question I had was, so I'll uncomment it. So we wrap this operation that we want to look like it's atomic and this operation inside block statements. And it's incorrect to say that we're locking this, okay? Every object in C# has a lock associated with it. And so when I say lock this, what it means, acquire the lock associated with this. It doesn't lock access to this. What it does is synchronize access to what's inside these braces. So what that says is, when you hit this lock statement, you must acquire the lock associated with this. Once you have it, then you can execute in here. Once you exit, you release the lock. So what happens if one task is running along and gets to this point, the other task is running along and gets to that point, and they both try to acquire the lock? Notice it's the same object, so it's the same lock they're trying to acquire. Yes?
They can't acquire it until the next one is released.
Okay, they can't simultaneously have the lock. The way the locks work is either one will get it or the other will, but they both can't have it at the same time. So let's say that decrement wins and acquires the lock. What happens up here with increment? Yeah?
Oh, it stops.
Right. It blocks. It's called, the thread has to stop, the task has to stop and wait until it can acquire the lock. So basically, that task gets put on a queue associated with the lock, and when the lock becomes available, that task is notified, and then it can continue running. So it suspends operations until the lock is freed up. And it's important to note that it doesn't sit there and use up machine resources, use up a core while it's waiting. It's not a busy wait. It's just put on a queue, and it gets, when the lock is available, it's total. It starts to run again. So that means that only when you have a pair of locks, like where you have this structure here, it means that only one thread at a time can be executing inside these two locks. So one thread only ever tries to increment, the other only tries to decrement. So it just means that only one thread at a time can be incrementing or decrementing. Yeah.
When you say lock, it's like lock to the object?
No, it's just, the way it works is, imagine C# just has a hash table of locks. And the object address is the key over there. The objects just provide a simple way to name a lock. So you're not locking this. You're locking the object associated with this. You're acquiring the lock associated with this. It's just, you've got to have some way to name locks. This is how C# chose to do it. So anytime one thread gets inside this critical section here, this block of code that's locked, the other thread cannot enter that critical section until it acquires a lock, which won't happen until this thread finishes with what it was doing. So that in that case, they really do take turns incrementing and decrementing, and we get the answer we would expect. So if we run it now, you see, they're not alternating exactly, and it takes longer because the locks have overhead, but you do end up in the same place. All right, so this is a simple example of synchronization. Yeah?
If you had a different variable you wanted to also be locking, you would still say lock this and then just reference a different variable in the braces. They would operate independently.
Yeah, well, so this is a very simple example. There are more complex situations where it's a hard problem deciding how to synchronize. But yeah, if you had a third critical section that you wanted to synchronize the same way, say there was a third operation that was being done, you could do the same trick. Now, what I put there, the object whose lock I'm using doesn't have to be this. It could be something else. So for example, here, I'll create an object. So I'm creating a private object called sync, just so I can utilize its lock. That's all I care about that thing. Oops. Well, actually, what if I did it that way? What if I lock this critical section with sync, and I lock this one with this? Yeah?
They wouldn't sync up because they would be able to just grab their...
Right, now they're independent. The decrementing method can always acquire this lock because no one else is trying to get it, and similarly, the incrementing method can acquire this lock. So it's like we haven't done anything except slow the program down. So it's important in this case that we use the same lock. It just has to be something, has to be an object that's shared by the two tasks. So why is sync shared by the two tasks? Why is this shared by the two tasks? How do we know? Yeah.
Is it like a key, as you said earlier, they're both sharing this key?
Well, it's a key, but they both have to be able to, we have to be able to reference sync. Why can we reference sync here? Where's sync declared? We can reference sync there, we can reference sync there because it's declared right here. Right? Now I made it private because it's not needed outside the class. I made it read-only because I don't want the value of sync changing. If someone changes sync, then the lock stops working. Yeah?
Is it because they are both methods associated with the same object?
Right, they're both methods associated with the same object. So what happened up here when I ran it? I called this.increment, this.decrement. So I called both those methods on the same object, and so of course they're going to have shared access to this instance variable right here. And so then I can refer. The reason total was a problem also is because up here I called increment on this and decrement on this, so they're going to share access to total. Because that's a property of the object. So typically tasks are going to share stuff on the heap. Some stuff on the heap. Okay? So this will still, even though we're locking with sync now, it's going to, it'll end up at 0. Okay? All right, so this is not an easy topic. We're just, we're going to look at simple examples of synchronization. Lock is sort of the simplest form of synchronization. You can use it to build more interesting synchronization mechanisms. But, you can do a lot with a simple lock. But you've got to understand, first of all, why locking is necessary before you can understand how you do locking. Why is, synchronization is necessary because fundamentally the reason is two tasks can be simultaneously operated on the same object on the heap. What do you think would happen if two threads were simultaneously adding to a linked list? If you're lucky, you get duplicate entries. A lot more could go wrong. What could go wrong if you're simultaneously two tasks are banging on the same list? Yeah.
Overriding?
Well, they're overriding each other, but what would be the outcome? Yeah.
You might link to something that's not in the list.
Yeah, the object can become corrupted. You know, think about what happens when you're splicing something into a list. You've got to take this reference and point it to this thing, and this reference and point it back to that thing, and splice in the elements. So you're doing like 4 pointer operations trying to splice the thing in. Now suppose that while you're doing that, someone else is trying to insert in the same spot. And they're moving pointers around, and you're moving pointers around. What you're likely to end up with is not a list that doesn't contain one of the elements. You're likely to contain a list that won't work anymore because the references aren't consistent. So with a singly threaded program, you're not going to corrupt, if your list class is properly written, you're not going to corrupt the list no matter what you do. But if you've got 2 tasks simultaneously modifying a list, you better believe you can corrupt it to the point where it won't work anymore. You start just getting all kinds of weird exceptions. So it's something you have to take seriously when you're doing multi-threading. You've got to somehow synchronize their access to shared objects. All right, I want to look at a different one now. We're going to look at Synchronization 2. Set a startup object. That's what I was trying to do. Okay, let's look what it's doing. It looks a lot like the original one, except what I'm calling is the same method. I'm calling set n0 and set n1. So let's see what set does. So all set is doing is it is assigning value to total n times. So it's setting total n times. And then it gets done. But you've got 2 tasks doing that simultaneously. One is trying to store 0. One is trying to store 1. So what could go wrong? 2 separate tasks furiously trying to store their own value into it. How would you know if things went right? What would you expect the value of total to be when this is all done, when the 2 tasks both finish? Yeah. Hmm?
Would it be value?
Well, we've got in one case, one task is using a value of 0, the other is a value of 1. Right? They're sort of simultaneously storing zeros with one hand and 1s with the other. So what would you expect the value of total to be afterwards? Yeah.
Whatever you told total to be set to last.
Right, you'd expect it to be either 0 or 1, right? Whichever it got set to last. Can you imagine a situation where it wasn't either? Just like sometimes in the other example, total ended up not being 0. Can you think of a situation where total would be neither 0 nor 1? So again, what could go wrong? What can you imagine going wrong simultaneously trying to store? Maybe you don't think anything could go wrong, but what's your opinion? Yeah?
Nothing gets written in and it's a null.
Okay, maybe nothing gets written in. Well, those sets are being called 10 million times. So something will be written. You think of another scenario where it might foul up? If not, why not? It sure fouled up when we're doing incrementing. Why won't it foul up when we're doing setting? Yeah?
It's only performing one operation and it doesn't rely on any previous stuff.
Okay, so what he's saying, it's only one operation. It's not 3 operations as what increment was. Okay? So what you're assuming is that the act of storing to this property is indivisible. It can't be partially done. But imagine it was like this. Imagine if storing took 2 steps. In one step, it stored the high order bits. In the next step, it stored the low order bits for some reason. Now what could go wrong? Maybe a situation where the high order bits were all 0s and the bottom bits were all 1s, and you got something that's neither a 0 nor a 1. That's certainly a possibility. Well, it turns out that this particular operation in C# is atomic. It's not divisible. Generally speaking, you have to read the fine print for the full rules, but reads and writes of things that are no bigger than the machine width, so like 64 bits in a 64-bit machine, are going to be done atomically. Things that are longer aren't guaranteed to be done atomically. So you're safe here. There's no need to do the locking because it's already, it's just, well, what makes it so that it's safe? What makes it so that storing into total is thread safe? Yeah?
You're not using the previous value of total.
Well, you're not using the previous value of total, so there's not multiple steps. But what makes this single write atomic? What is it that makes it atomic? Yeah?
Would it be the fact that it's 64 bits and it can handle that size in one step?
Yeah, well, yeah, it's because, yeah, it has to do with the processor. It's just the processor does it in one step. And it has to do with the way the memory system relates to the multiple cores. But it's just a property of the computer it's running on, and the way C# uses that computer. So it's guaranteed to be atomic. So very low-level things, if you're just reading and writing them, give a single read, a single write, you're going to see consistent results each time. It's not going to conflict with each other. Now, let's look at another one here. What have I done here? So this is the same example, increment and decrement now, back to the original one. What do you think is going on here? What the heck is interlock.increment ref total? Yeah?
So link two things together so they perform at exactly the same time?
Well, it's not linking two things together, no. That's a reasonable guess based on the name Interlock. I'll grant you that. Yeah?
The value, whatever method is running, it returns the value in total, but it also has access to total.
Well, we're passing a reference to total to increment. Yeah?
Asking for the lock associated with total.
No. No. What do you think it would say if I hover the mouse over increment right there, that increment method? Let's see. Well, it doesn't say anything. Okay? So we just have to suppose what it says. Basically, it's a thread-safe way to increment the parameter. So interlock is a class in C#, and one of its static methods is increment. It takes a reference, in this case, to an integer variable as a parameter, and it increments it in a increments it in a thread-safe manner, or decrements it in a thread-safe manner. So C# doesn't leave you all alone in the woods saying, you know, any multi-threading you do, you're going to have to use locks. It provides some other primitives to use. Lots of ways you can deal with multi-threading. So if you need to safely increment and decrement in a thread-safe fashion, those methods exist. They do their own, maybe they have internal locks that they're using, or who knows how they're implemented, but they do it in a thread-safe manner, so you don't have to explicitly lock yourself. Now, it might be interesting to see, I'm not actually sure what I'm going to see if I do this. You know, so we can see there's a decrement, there's an equals, an exchange. What do you suppose exchange is? You had to guess. Yeah?
Swap two items in an array
Yeah.
or list.
Swap the values of two variables. Reference equals, add, and so on. So there's a handful of thread-safe methods you can call. That's one example of something that's built into C# to make your life easier. Yeah?
So that interlock increment is calling a different increment, not this method.
Correct.
Okay.
Yeah. Interlock is a class, increment is its static method. Yeah, it's just a coincidence that these two methods are the same. That name, but these are methods of different classes. So this isn't, it's not like we're applying the interlocked operation to increment. We're calling the increment method in the interlocked class. And it's a thread-safe way to increment a variable. So if we run this now, it ought to work like our original one did. finishing at 0. Okay. Okay, so yeah.
Is there a reason that one never got negative, became negative?
Okay, he's asking, is there a reason it never became negative? I think it's just chance. Sort of depends on, there we go, which thread gets ahead of the other, which task gets started faster, whatever. Any other questions? I'll move to a different set of examples. So I'll wrap up any question you have here. The key concept here is thread safety. So here, these two methods are thread safe because we're using these thread safe primitives. These two methods are thread safe because we're doing explicit locking to synchronize access to shared resources. And the other one is thread safe. For what reason? What makes these two thread safe? What makes set thread safe? Why can two threads be running set at the same time? Yeah?
Is this a smaller operation?
Right, because it's just using a primitive operation that's just guaranteed to be atomic. It's simple enough operations are atomic. Reads and writes. Yeah? Yes?
When you're designing code using threading, should you start out considering using threading, or is it something that you should incorporate when you're optimizing?
Okay, that's a good question. Do you start out thinking about threading, or do you add it later and think about optimizing? Well, the case where you might add it later is if you're not getting sufficient performance and you want to harness multiple cores. But there's another circumstance where you use multitasking, which is when, we'll see an example shortly, when one thread has to wait for another thread to finish. So we do them for waiting purposes. So certainly when you're having multiple tasks for waiting purposes, you design it in from the beginning. No way around it. The other situation where you're trying to speed up some CPU-bound computation, I can see that being an optimization. It's certainly easier to get a slow version working and then make sure you at least got the algorithm debugged before you try to run it in parallel, because that get rid of the simple bugs before you start introducing the multi-threading bugs. Yeah.
So can you steal all the resources from your computer to make your program run faster?
Okay, he asked, can you steal all the resources from your computer to make your program run faster? Well, here's the thing. The operating system, its job is to run processes. So when you create a multi-threaded program, it's a single process to the operating system. So the operating system decides which processes get which resources. So the operating system will decide, this process over here really needs a couple of cores, I'll give it 2 cores for a while, and then take them away. And so no, you couldn't steal the whole processor without the cooperation of the operating system. Within the process, we're talking about the C#, the .NET runtime system. So it's the one that decides, using the cores given to it by the operating system, which tasks should it run for how long and when. So it's decided at 2 levels. Any other questions? Yes?
So once the operating system gives the .NET runtime a certain number of cores, does .NET have all of those cores until it's finished the program, or is Windows going to take them back every now?
No. You don't get the cores forever. Essentially, when .NET gives you some cores, it says, here, you have these cores, and then after a certain quantum of time has passed, it may take them away and suspend the whole process and let some other process run for a while. Or it may be they're so lightly loaded it just lets your process keep them. So in a heavily loaded system, when you've got all these processes contending for the cores, then you end up with, your program runs in fits and starts, like as if it were only a single core machine. Yeah?
Does each individual core handle a 64-bit size number?
Oh yeah.
Okay.
Each individual core is a processor of its own.
Okay.
It's just sharing memory with other cores. Now, here's something to think about. Multitasking is useful even if you only have one core. Why is that? Why would you want to do multitasking if there's not multiple cores to exploit? Yeah?
I mean, like you said the other day, if you're running a GUI or something and
Okay? So the bottom line is it's a useful abstraction. You can, it can be convenient, especially when you're talking about tasks whose job it is to wait for other tasks. Is to split up the work into multiple tasks, even though they can't run simultaneously. They can run sequentially. And we'll see examples where even if there was only one core available, you'd want to split up the task, split up the work into multiple tasks, just because it's easier to work with, easier to think about. So let's keep an eye open for when that happens. All right, so I want to move up now to this thing called max factor count, and we'll look at what it looks like. Okay, so this is called the driver program. So what it does is it creates a new max factor count object. It starts a stopwatch. It calls max factors of whatever that number is in 7. And then it stops and prints out how much time it took to run. Now, what find max factor is looking for is the number between 1 and, in this case, 120,000 that has the most factors. Just trying to find the number less than that has the most factors, and it's going to use 7 cores to do so. And so if we run it, it'll take a while. And so in about 6 seconds, it found out that 110,880 was the champion with 144 factors. So factoring is the way I've implemented it anyway. Well, in general, factoring is slow. Mine is about as slow as it can get. But that was with 7 cores. So if I used fewer, it would be slower. Okay? So how do you suppose this method here works? What's it doing? What would it look like if we looked at it? Yeah?
Probably splits the process of factoring into 7 different threads.
Okay, it's this. It would do the trick we were doing with prime numbers. So let's look at it. Uses multiple tasks. So it's creating an array of n tasks, in this case 7, parameter is 7. And then it goes through this loop, and you see down here, it calls tasks.run. So it creates, each time through the loop, it creates a task by giving a delegate. And what that delegate does is it calls find max factors in interval, and it's tasked to begin, and then it end tasks. Not sure why we're passing end tasks to it, but I don't think it's necessary. So it's just firing off those 7 tasks. Then what happens? Now the 7 tasks are all running in parallel. What's happening down here? So each one of those tasks is going to produce a result, namely the champion for the numbers that it looked at. So they're slicing out, each is looking at 1/7 of the available numbers. So what's happening down here now? Where it says find and return the best result found by the tasks. How's that working? Yeah?
Is it checking the individual tasks to see what its champion is and then comparing it to the other ones?
Right. So it's looping through all the tasks, and it grabs the first task. Remember, tasks is a list of tasks. It asks that task for its result. Now that may block for a while, because it has to wait for the task to be done to get its result. But it gets its result. It finds out, so now it knows which of that tasks, what that task champion was. It figures out how many factors that champion had. And if it's better than what we've seen so far, it updates these numbers. So it loops through all the tasks as they finish, updates those, and then returns the overall champion. So we got 7 tasks out looking for factors, and we got this other task that basically blocks for 5-6 seconds until the first task finishes, and then it finishes up pretty quickly and returns the result. Okay? Is there any synchronization necessary here? Let's look at the method. This is the method that's running. Oh, I see why I'm passing a number of tasks. That's just splitting it up. It's just at every 7th number. But that's just accessing local variables and parameters, right? Low, high, delta. None of them are objects that could be shared from the heap. So no synchronization necessary. They just run flat out, and then the main task is going to merge the results in after the task's finished. So that's good. Now, I want to turn your attention to a detail that really has nothing to do with multitasking, but it's important to understand. So here is my for loop here that's firing off the tasks. What's that for? Why do I say begin equals I plus 1, and then I put begin right there? Why not just do this? Why not just say I plus 1? Why do I create a variable called begin and then pass it? I'll give you a hint. They're not equivalent. What I have right there now won't work. Yeah?
Reference problem?
The what?
Reference problem.
Okay, can you explain what that is?
What's that number? Some reference?
Okay, so you're not the same reference. I think you're getting at it, but I'll use different words. Yeah?
If you put it in there, each task increments its own I once, compared to begin always being the same for all of them.
No, begin is different for all of them. So that first parameter is a starting point. So task 0 gets a starting point of 1. Task 2 gets a starting point of, task 1 gets a starting point of 2, and so on. That's how we split up the work. Yeah?
Every time it calls the find max factors in interval method, it adds I to 1.
Okay, that's true. So let me nail this down. When do you think I plus 1 is evaluated? When will that addition happen? Does it happen when the task is created? And if not, when? Yeah?
It happens after something gets run? Or something
Wait,
gets
it does.
performed?
That I plus 1 is not evaluated until this delegate is run. So when we call task.run, it's got to set up all the task mechanism. And once that's all set up, then it calls that delegate. And when you call the delegate, the first thing it's going to do is evaluate I plus 1 and then pass the result to find max factors in interval. So the I plus 1 is not done until the delegate's evaluated. Okay? So when the delegate is evaluated, when it's called, where does it find I? It's just a method. Where is it going to find I? I mean, where can it go to look up I? Yeah?
Is it from the for loop?
Yeah, it goes, there's a stack frame where the delegate was created, and it goes back to that stack frame and looks up I. But by the time that delegate runs, what do you think the value of I is?
It's changed.
It's probably changed. It's probably, if in task is 7, probably what's going to happen is that loop's going to run really fast. It's going to call task.run 7 times, and at that point the loop will end and I will be 8. And by the time the loop runs, then the delegates start running, and every one of them, when it looks up the value of I, will get 8 as the result, because they're all looking at the same I. People make this mistake all the time. I make this mistake all the time. And it's hard to diagnose. But believe me, if I can run this. I don't remember what the answer was originally. Let's see if we get the same answer if I run it.
It was like 108,000 or something like that.
Okay, we got a different answer. Simply because all those tasks were probably searching the same interval, because they all saw the same value of I, because they all referenced the same variable I, whose value had changed before the delegate was evaluated. Yeah.
So that kind of looks like a believable answer off the top of my head. So how do you go about like diagnosing that that's the wrong answer?
How do you go about diagnosing it's the wrong answer? It is hard. Bugs in multi-threaded programs are really hard to find. You'd have to know what answer you're expecting. So presumably you would run it in a singly threaded program and find out what the answer is, and then notice that it's wrong. But yeah, there's nothing, you look at that and you don't say it's obviously wrong. So back to this, how did I fix the problem? By putting begin here, that make any difference? And this is where you really got to understand how programming languages work. Yeah?
It's called before task not run.
No, that's not exactly it.
Begins on the stack.
Okay. Remember, what happens is, when this delegate is run, it goes and looks up begin in the stack frame that existed when it was created, when the delegate was created. A new stack frame is created every time that the body of the while loop executes. So when the while loop executes, a stack frame is created. Then the next iteration, that stack frame goes away and a new stack frame is created. So each delegate is created. When each delegate is created, there is a different variable called begin, a different stack frame containing begin. So all the delegates refer to different variables called begin from different stack frames. The problem with I is it's declared outside the loop. It's in a stack frame outside the loop. It never changes. And so all the delegates look at the same I, but at different begins. So whether you understand this explanation or not, and I very understand if it seems mysterious to you, just realize that if you write a delegate that contains variables declared, all three of those variables are declared outside of the delegate. You got to think about it. If one of them is a loop variable, in particular, that's changing, if you're doing something in a loop like this, you need to do something like that instead. Make sure that you're getting the value that's being updated in the loop from a local variable. It's a very common source of errors. Okay? This is a difficult topic. Yeah?
So if that's all happening, is the for loop waiting for them all to finish?
No.
It continues?
No.
Well, so how do I know down lower the result? Like the delegate is run?
The delegate, you know the delegate is run because this task down here, we get its result back. When we add the task or its result, that operation will block until the task is finished and can give us a result.
That was the question.
Now the questions no one's asked is, I said when that loop is running, it creates a stack frame to execute the body of the loop in, and then it throws it away and does the next loop, next iteration. Throws it away, does the next iteration. Remember, it's being popped and pushed, pushed and popped, pushed and popped, pushed and popped. What's the obvious question I haven't answered? Yeah?
Where does begin go in the stack?
Yeah. We got these 7 tasks that each refer to a different stack frame, but what if they've all been popped? Well, the answer is a C# has to keep track of it. It gets popped off the runtime stack, but if it knows a delegate's referring back to it, it has to keep it around somewhere else. And that's such a pain that a language like Java won't let you do this. In Java, you can't have variables, non-local variables inside a lambda. They have to be, if you do, they have to be constants. So Java isn't as powerful in the C# is in this case. But it's easier to implement and easier to understand. All right, just remember that as a potential source of problems if you write a loop that's calling delegates. All right, let's take a break and we'll continue looking at aspects of multithreading. start again. Okay, I want to drive this point home here. So I'm going to take out the begin. I'm going to put in the I plus 1. And then I'm going to go to find max factors in interval and print out the value of the first parameter when it ends up being called. Okay? So I'm going to highlight it here so we can miss it. And we'll print out the value of low when it's called. What did I do? Isn't that the right way to print something?
Curly braces must be missing somewhere.
It's possible you're missing a using.
Well, but I do print line elsewhere. Console.writeLine, right? Oh, you're right. I am missing a using. Thank you. That was a minimal set of usings. Okay, so back to this. Ideally, we would see that one task will print out 1, another task 2, 3, 4, 5, 6, 7, getting us different start points because we're passing I plus 1. Let's see what happens. They all saw 8 because by the time the task starts running, I's value is 8 by that point because that loop is finished so fast. They all refer to the same variable I. That's baked in. What variable they refer to were baked in when they're created, but the value of that variable could change between the point in time when the delegate is created and when it's evaluated. If we do it the begin way, now what do you notice there? It's a little screwy. Yeah?
The 6 is out of order from the others.
Yeah. The 7 delegates were created in order, but it turns out that the one that was created 6th started running 2nd. Okay? So that's just price of business. All right. So again, this detail is not. It's something that has to do with delegates containing non-local variables in their definitions. It's not something about multi-threading per se. It just shows up, happens to show up here. Yeah.
So if you put a lock around that task array, would it evaluate before it goes on to continuing in the loop?
No, lock wouldn't help here. Okay, let's try this. I'm in an experimenting mood. So let's go back to I plus 1. Let's create the task. It's not task.sleep. It's shucks. I don't have enough users here. So let's sleep for half a second. Hopefully you can tell me. All right, who remembers? I saw that before. Was it task.sleep or thread.sleep?
Thread.sleep.
All right, and hopefully it'll know how to import. Okay, using system threading. Okay. So how might this solve the problem? If we pause, if we basically stall the loop for half a second. Yeah?
The delegate will definitely finish computing before.
Well, it's not that the delegate will finish computing, it will have a chance to start running.
Yeah.
And so it will have time to look up the value of I before I changes. Okay? Maybe. Okay. So now it works because we slow down the loop. I mean, that's not a solution because it slows everything down, but it shows you that the problem is they're all referring to the same I. If we arrange so that it can look up the value of I before it changes, it works. Yeah?
So if you're going through 120,000 numbers and you're pausing for half a second between each number, why didn't that take 60,000 seconds?
Oh, I'm not. I'm pausing half a second between what operations? Before I create a task and set it off to run, and then I pause. So I just pause after each task creation.
So each task is doing 1/7 of all of
Right. The cost there is the first task gets to run like before. The second task has to wait half a second before it gets going. The third task has to wait a full second, and so on. Okay? You wouldn't do that, but it does, it illustrates what's going on here. So you definitely want to, I'll put it back like this so when you look at it later, you do it the right way. But I'll put this here. No, not that there. This here, so you remember what I did if you want to replay it. Okay? All right, any other questions before we look at the next version of this program? Yeah?
When would that be a good idea?
When would what be a good idea?
Like using sleep instead of making in begin?
The only time you want to use sleep is if you're doing a loop that's busy waiting. That's waiting for something, like it has to print something. If you want to, it's not even if it's, we saw the example before, we wanted to print out an update every half second. So that's one way to do it. But I could have done without that. There are objects called timers that will call a delegate every half a second. That would be a cleaner way to do it. Usually if you find yourself adding sleep calls into your multi-threaded code to make it work, you're playing with fire. Because it may work now, but it may not work tomorrow when your computer is loaded differently. Yeah, so don't look, it's generally not a good idea to try to fix problems by artificially slowing down your threads. And I'll just keep repeating, this is hard stuff. People have been studying multi-threading for a long time, trying to find out with, ways to do multi-threading in a way that people can deal with in their brains, and it's just hard. It's a lot harder than normal sequential programming, which is hard enough by itself. So don't feel discouraged if this seems all kind of baffling, because that's how it appeared to all of us when we first saw it. Okay, and so we were looking at max factor count, and you'll notice down here, this is the method we were calling that actually does the factoring. And what it does is periodically call update statistics. So we've got a thread, a task that's evaluating that thing. So it's looking at some slice of the numbers, and it's just iterating through them in that outer for loop, and occasionally it calls update statistics. Okay? When does it call update statistics? Yeah?
When it finds a number with a greater amount of factors.
When it finds a new champion. So this thing is looking, every time it finds something that has a higher count than it's seen before, it updates the count, it updates the number of factors. So it knows the number. Well, no, it updates the number of factors there. These are badly named variables. It stores the number there. And then it calls update statistics to tell the world, hey, I found a new champion. Now, update statistics doesn't do anything in this method. Now, what I want to do is change update statistics, and that'll be in max factor count print. I want to change it to anytime any thread calls, any thread finds a new champion, I want it to be printed out. Right? So let's see how that works. All I'm doing is I'm overriding this update statistics method. So I have a global for across all threads, the current maximum number of factors and the current best number. I got those backwards because of the bad names. So if some task has found something that's bigger than a thread than any other task has found, we print it out. So we can see them building up to the eventual champion. Okay? So they're all going to call this one method, and they all share, all threads are simultaneously calling update statistics. Update statistics has these instance variables, they're shared across threads. And when we find a new champion, we print out the result. What could go wrong? Or is this going to work? So seven tasks running. When they find their own new champion, they call update statistics. They're all calling the same update statistics. And update statistics, if it's better than anything it's seen before, it prints out the new champion. Yeah?
Each one will think it's found the next best thing.
Well, yeah, the task will find the best it's seen and call this method. And if it's better than anything anyone else has seen, it'll get printed out. That's the goal. Yeah?
What if, like, so these are looking at different numbers at the same time, right?
Well, update statistics can be called simultaneously on multiple threads, yeah. It can be, yeah. Sure. If this task finds its new champion at the same time this task does, and it's not done yet, it's found something bigger than it's ever seen before, they could both call update statistics at the same time.
Well, if a bigger number gets found slightly before a smaller number, the smaller number never gets printed.
Okay.
The bigger number does.
Right. So we have simultaneous access to this code. The two tasks, there's variables shared across the code. So we may see the statistics not go up. It may go down at some point. So let's run it and see. So to do this, I have to go back to the driver and have it create a different counter, the one that overrides it. Oh, the only difference is we've overridden update statistics. All right, so let's run it. So it's printing out the champion. So it goes 5, 12, 40, 96, 180, 240, 36. 600, 720, 1080, 14. So how did 14 get in there? It's only supposed to be printing that, that update statistics is supposed to print something out when it's bigger than anything it's seen before. Something screwy is going on. We should just see those numbers going up. Yeah?
My guess is specifically with the 14, that would be the last thread that got created, because it would be the 7. So that's probably the first one that thread's run into. And it called that right at the beginning.
So it found that 14 early on, and it called update statistics. And for whatever reason, because there were multiple threads accessing at the same time, it got counted as the new champion, even though there are already numbers that had been found bigger. Or maybe that thread ran early. It found that 14 early, but it got delayed, then it called update statistics. Update statistics decided it was a winner, and then the thread got delayed, and by the time it could store the new statistics, the other task had raced ahead and found something bigger. I want to see these numbers go up monotonically. I don't want to see them. I want to see the current champion, and I'm not seeing that. So how do I fix that? While you're thinking about that, I'm going to go find where I print out this and take it out. Okay. How can I fix this problem with this method here? How can I make it thread safe? Yeah?
Would you lock it?
Yeah, I just need to wrap a lock around the if. So only one task at a time can be in there. The problem right now, multiple tasks may simultaneously test that and pass it, and then you got conflicting updates here. Who knows what's going on? So let's go to this one here, which is a version that, this version of update statistics just sets a lock and then calls the method we just looked at in the base class. So this class extends the class we just looked at. So this is the plain old update statistics. This synchronizes access to it. So only one task at a time can be updating its statistics. So back to driver, we'll change it to create a different counter object. Now we're doing the sync version. We run it, and they just go up. No, they don't. 288, 240. That's upsetting. Oh, okay. It's not the numbers that go up. It's the second number that goes up. So this is the number that keeps going up. 2, 4, 9, 16, 18, 20. I was looking at the wrong number before. Okay. So we got it straightened out. So now I want to make sure that my original was really failing. Okay. False. So let's run it again. 3, 4, 27, 9, 30, 32, 20, 12. Yeah, so it's definitely failed. Okay, so that's just another application of synchronization. You got to be able to recognize the problem before you do anything else about it. Now, let me pose the following problem. Maybe you get bored waiting for your program to finish running, and you just want to tell it, stop. Stop looking. You want to stop all the tasks. Now, one thing you could do is just, Control-C, kill the window, whatever. I want to shut it down gracefully. How do you suppose we could do that? How do you think we'd get these tasks to basically tell all the tasks, quit? Stop where you are and return right now. Yeah?
Java had a thread.kill. I'm not
Okay.
sure if C# has a similar.
Okay. Java has a method called thread.kill. You can kill a thread. It's been deprecated for the last 20, 25 years. They put it in version 1. They quickly realized it was a mistake. So they kept it deprecated all these years. You're not supposed to use it. Well, what's wrong with just letting one thread kill another thread? Yeah?
Was it because there was only one core at that point?
Well, it didn't have to do with one core, no. It had to do with, you don't know what that thread is up to right now. Suppose that thread is in the middle of modifying a database, or in the middle of writing a file, and it gets killed right then. That leaves the file in some wrecked state, because it's incompletely written, or the database is compromised. So it was realized that letting one thread, letting a thread be killed by an outside force, yeah, you can get rid of the thread, but it may leave damage behind when you kill it. Incidentally, you'll find that the words that are used in multithreading are kind of violent. Kill being one example. So, what's another way if you can't kill a thread? Yeah?
You ask a thread to stop.
You ask a thread to kill itself. And so so essentially, if you are creating a program and you have long-running threads, and you want them to, you want to be able to interrupt them, ask them to stop, you got to design that into the design of the program the thread is running. It has to periodically check and see, have I been asked to stop? Okay? So how would we do that? We're going to go to max factor count with cancel. So it's the same idea, but it has cancellation built in. So let's make this the new startup project. Get rid of all this stuff so I'm not confused. And here's our driver. So let's see what our driver looks like now. I've got to, well, I'll just leave it on that version. So I'm still calling find max factors. But look what I do now. Find max factors, I create an instance variable called cancel that's set to false. I fire off all those tasks like before. I fire off another task whose job is decide whether or not, its job is decide whether or not to cancel those other 7 tasks. And then the rest of the code is just like before. So what do you suppose that wait for stop request method does? Given this is a demonstration of cancellation. Yeah?
It votes for a certain key to be pressed, and then it says cancel the true.
Right. So what it does is, let's go to the definition, it just blocks. Okay? Now this is a simple command line program. In a real, say if this were a GUI, you'd probably have a cancel button. And when the cancel button was clicked, then the code for that button would set the cancel variable to true. But just to keep this simple, we're creating a task that immediately blocks until the user hits enter on the console. And if the user hits enter, it sets cancel to true, and then that task is done. So that task is not there so it can run useful computation. It's there to wait for the user to type something. Probably not the best example of a thread that just immediately blocks, but it gets the idea across. Yeah?
You ever have problems where, if you have, say, 6 cores, and you have 6 cores available, 6 are being used when you're programming it, oh, he's at 7th core.
Yeah.
He's on that cancel one. You have any problems there?
It could take a while. If, you know, this thing may not run instantly once this happens. But what's happening is this is not occupying the core. As soon as it hits that block waiting for an IO event, this thing is, the thread this is running on is taken out of the core, is suspended. Then when that event happens, the runtime system notices and says, ah, now I can resume this thread. Then it takes a core.
Okay.
So just because you create a task doesn't mean it gets a core. And when a task blocks, it gets out of the core until something happens to unblock it. All right, so its job is just to set true, cancel the true. Now what happens if we never hit enter? What happens to that thread? That task, I should say. It's waiting in vain for a return to be hit. What would we like to happen? Let's say all the other tasks are done. The main task is finished. And there's still this task waiting for us to hit enter. What would you like to have happen? Yeah?
Just have it stop waiting.
Just have it, yeah, basically have it stop. And that's what happens when you create a new process and there's multiple threads. The question becomes, when does the process terminate? And typically there's one or maybe multiple threads such that when they all die, when those threads all complete, the process is over, even if there are other threads still running. So in this case, as soon as that main thread completes, this thread will be abandoned by the runtime system because it's not deemed essential. It's meant to be eliminated once the program terminates. Okay, so that's where we set. Where do you suppose cancel is used? So we're back up here. We are calling find max factors in interval. How does find max factors in interval make use of cancel? You've got 7 tasks all running find max factors in interval on different parameters. What do you think? How do they cancel themselves? How do they know when it's time to quit? Yeah?
Immediately after they finish the current process they're on? Or?
Okay, it's hard to guess, but we'll go look. So notice we got this loop here. This loop is just iterating through all its numbers, looking for factors. Every time at the top of the loop, we check. If we've been told to cancel, we just return 0. We're done. So if that ever gets set to true, whatever we're in the middle of doing, we just abandon it and return 0 as our result. So that's how you cancel. Now, do we need to put locks around cancel? Because we got one task that's setting it, and we got 7 tasks that are reading it all the time. Is that a possible problem, that shared access to cancel?
Yeah. No.
Conceivably, but why not? It's actually not. Yeah?
Is it atomic?
It's atomic, yeah. So generally speaking, like I said at the beginning, if it's machine word size or smaller, reading and writing it is atomic. So certainly, again, that's only roughly speaking. It depends on some technical details. The language has to make sure that it obeys. But in this case, yeah, setting and reading a Boolean is atomic. So a lock here would be overkill. All right? So let's run this and see it in action. So I'm going to do Control F5, then I hit Enter and it's done. All right? And it displays 0 as a result because I didn't work too hard on the program. That's just what that's what all the tasks return. When they cancel themselves. Okay? So that's another example of a task, that waiting task. This job was just to wait for that event to happen. And then it did the cancellation. Now I'm going to look at one more. I want to see if there are any questions about this one before we look at another. All right, this one is called max factor count cancel token. All right, let's see what this one is. So it's like the one above. Here's our driver. And let's see what we got. What's going on right here? turns out that cancellation is such a common thing to want to do that the .NET library provides something called a cancellation tokens. So a cancellation token is a shared object that's shared by all the tasks, and it has methods on it that lets one task say cancel, and then all the other threads can take notice and cancel themselves. So it's just a more systematic and actually a better way to manage cancellation than creating an instance variable called cancel, even though you end up typing more. So to make this work, we create a cancellation token source. So that's going to be the source of the shared tokens. Then we call wait for stop request, and we pass it the source. So let's go look at what that does. So we pass it the cancellation token source. When it reads a line, it calls cancel on the source. All the other tasks are going to have tokens created from that source, and they'll notice when the cancellation happens. So that's that. Other than that, we just call our find max factors. In addition to the usual parameters, we pass it source.token. So that's the shared token all those threads are going to use. So let's go look at it. Okay, it gets the cancellation token. When it fires off the tasks, it passes the same token to each of these things. So what do you expect you're going to see in find max factors and interval? How will they be making use of the token? They'll be checking it in some way, right? See if it's time to quit. So let's see where that happens. Right there. So that's kind of a neat thing. When you want to cancel yourself, you just call this method token.throw if cancellation requested. And if a cancellation has been requested, then this thing throws an exception. It throws a particular exception. And the cool thing is, the task that's waiting, back in the main task, we're waiting for all these other tasks to finish. It will see the exception propagate out of the task into its task. So if we have canceled, we're going to throw an exception. So let's go back to where we started all these tasks and look at what happens. So I've written the code a little bit differently here. Right there, I'm waiting on all the tasks to finish. And I pass that token to wait all. So one reason to use cancellation tokens is there are lots of built-in methods that have the cancellation token. And if I cancel the token, wait all will cancel itself. And then down here, what that will do is it'll throw the operation cancel exception if that happens. So if I cancel, I'm going to get an unhandled exception. I could catch it. So let's run it and see if this works. All right, so operation canceled. Somewhere that thing got, so wait all through the exception. So back in the driver, it got called, and it says operation canceled. So to summarize, cancellation is simple. You just got to write a method to check to see if it needs to be canceled. It's better to use cancellation tokens for a number of reasons. One is it gives you a clean way to cancel by throwing an exception that can be called. And also cancellation tokens are used by other things like wait all that are provided by .NET, by the C# library. All right, so that's a lot to think about. Yeah?
Going back to the previous example with the wait for stop request method, how were you able to, where you like manually entered, we're checking for cancel, how were you able to stop all the tasks from running?
Okay, which example are you talking about?
The one where you had the method with, it was called wait for stop request. The one where you checked like console.readline and then if nothing was inputted, if it was enter inputted, then...
Okay, so right here is wait for stop request.
Yeah.
Okay.
So how were you able, well, without the cancellation token source?
Okay, without the cancellation token, it just said cancel equals true.
Right. But how did that stop all their?
It didn't stop, it just set that variable. Now, the method that was being run, the loop that was being run on all those other tasks, very first thing, each time through the loop, it said if, cancel, return. All right, let me tell you where we're headed now. Well, I'm going to have a little bit more to say about multi-threading, but we're not going to use it, by the way. So the next major topic we're going to talk about is GUIs, building graphical user interfaces. So the lab tomorrow involves GUIs, and of course your assignment 7 will involve GUIs. What we'll see when we start tomorrow is you have to understand something about multitasking to understand GUIs. Let me give you one reason why. I'll give you 2 reasons. One, GUIs run on a separate thread from the main program. So if you write a GUI, you already got two tasks. The other is, suppose you had a GUI that was calculating the number with the biggest factor, with the most factors. So you would click Start, and if you're not careful how you structure it, you might not be able to use any of the buttons in your GUI until it finishes calculating, unless you're using multi-threading. So what we just saw with cancellation tokens would turn into a cancellation button in a GUI. You want to structure a GUI so that long-running computations are done on separate tasks so that the main GUI task can continue running and making the GUI responsive. So we'll wrap up that loose end tomorrow and on Thursday, and we'll start seeing how to build GUIs.